Welcome! Caroline here. Today, you'll take on the role of an aerospace engineer. You've already learned how planetary probes explore new worlds. Some stay in orbit, some fly on by. But rovers and landers? They're designed to reach the surface and collect data. And to do that, they have to land in one piece. Since probes enter a planet's atmosphere at a high speed, engineers design systems to slow them down and protect something essential: the payload. That's the scientific cargo the mission was designed to deliver. On real missions, the payload might be a rover, a drill, or sensitive research instruments. In this lab, you'll design and test a model lander that protects a payload of your own: an egg. It's a stand-in for the fragile instruments that real landers carry. Let's start by taking a closer look at how engineers approach challenges like this. Engineers don't jump straight into building. They start with thinking. For today's lab, you will use a method called the engineering design process to guide your thinking. It's a step-by-step method that can be used to solve problems. Step 1 is to identify the problem. Your goal in this lab is clear. Design a lander that protects your payload, the egg, as it drops to the surface. But what counts as success? Ideally, 3 things should happen. The egg remains unbroken, the lander hits the target, and the lander stays upright. Just like in a real mission, missing any one of these could mean total failure. Let's think. What actually causes a payload to get damaged during landing? Even when a lander is moving slowly, making contact with the ground creates impact force, a sudden jolt that can crack, crush, or flip the entire structure. That's why many real-world landers include shock-absorbing materials or designs that cushion the impact. Just like airbags protect passengers in a car, these systems help spread out the force of landing and protect the delicate equipment inside. Your challenge is to do the same. Protect your payload using materials or designs that reduce the impact force. What are your options? Well, before engineers start coming up with ideas, they need to know their limits and the requirements they have to work within. Here are your guidelines. Your payload, an egg, will be placed inside a small bathroom cup with another cup stacked on top. These cups represent the outer shell of your lander. You can't remove or replace the cups. Any cushioning you add has to fit inside or around them without making your lander huge or complicated to assemble. So, now that you know your design limitations, what's the next step? It's time to brainstorm solutions. What kinds of materials or designs could help cushion your payload and absorb shock during impact? Pause the video and jot down as many ideas as you can. You may have thought of soft materials like foam or cotton, or flexible materials that bounce or bend. Those are all great ideas. Make sure you save those thoughts for later, as you may want to try them out soon. But before we try those out, I went ahead and selected a design for you to build first. This will give you a good starting point for your lander. For this starting model, we'll be using cotton balls and flexible straws as our cushioning system. Before you continue, pause here to read over the safety information, materials, and lab procedure in your interactive lab notes with a parent or guardian. Make sure you have their permission and all the required materials before continuing. Now that we have a design idea and some materials to work with, it's time to build a prototype. A prototype is just an early version of your design. It's something you can build, test, and improve later. Engineers build prototypes to see how well their ideas work in real conditions. As I talk you through the steps, feel free to pause the video if you need more time, or rewind if you want to watch a step again. And if you're not able to do the lab at home, that's okay. You can still follow along and record the data you observe. Let's get started. Begin by placing 5 to 6 cotton balls into each of your bathroom cups. These will act as the inner cushioning. Next, take your egg and gently wrap it in cotton rounds to give it an extra layer of padding. Once it's wrapped, place the egg into one of the cups right on top of the cotton balls. Then take the second cup and place it over the top of the egg, like a lid. If there's still a lot of space around the egg, add more cotton balls to the top cup to make sure the egg fits snugly and doesn't rattle around. Once everything's in place, tape around the seam where the two cups meet to hold them securely together. Now let's add the lander's feet. Cut 3 bendy straws in half, then bend each straw at its flexible section to form an L shape. These will act like shock absorbers. Tape 3 of the straw legs evenly around the bottom of the lander. These should be spaced apart to help balance the structure when it lands. When you're finished, your lander should sit relatively flat on a table with 3 visible straw feet supporting it. Pause the video here if you need to finish your build. Ready to test? Let's see how it performs under pressure. Now it's time to test your lander and see how well your prototype performs. First, you'll need to set up your landing zone. Choose an area where it's okay to make a little mess, just in case your egg doesn't survive the fall. A hard floor that's easy to clean or a space lined with newspaper or towels works well. Next, designate your target, the spot where you want your lander to hit. You can use a paper plate, a large index card, or anything else that gives you a clear landing marker. This will help you test not just whether the egg survives, but how accurate your design is. Once your target is in place, hold your lander by the top cup, keeping it upright and steady. Raise it to about eye level, directly above your target. Then let go. No tossing, no angling, just a straight drop. Pause the video here if you want to go ahead and try it for yourself. After the lander hits the ground, take a moment to observe a few key things. First, look at how close your lander is to the target. Measure the distance from where it landed to the center of your target area. Record that information in your notes. Then look at how it landed. Was it upright? On its side? Upside down? Record that information in your notes too. Now comes the fun part. Open the lander and check the condition of your egg. Look for any signs of cracks, dents, or leaks. Even a tiny crack can be a sign that your cushioning needs improvement. Once you've made your observations, write them down. And don't forget, if your egg did break, make sure to clean up your workspace before continuing. Nobody wants to work in a sticky mess. Let's think for a minute about the data we collected. In an earlier lab, you learned about 2 types of data, quantitative and qualitative. You've just collected both types. Can you tell which is which? Which of your observations were measurements, and which were based on descriptions? Pause for a moment and sort your data into those 2 categories in your notes. The quantitative data is the information you measured, like how far your lander landed from the target. Anything that includes numbers like distance or height counts as quantitative. The qualitative data is what you observed using your senses, like whether the lander was upright or on its side, or whether the egg had cracks or stayed fully intact. These are descriptions, not measurements. Recognizing the difference between these 2 types of data helps scientists and engineers communicate clearly and make better design decisions. And that's exactly what comes next. Every observation you just made will help you in the next step of the engineering design process, evaluating your design and figuring out how to make it better. Now that you've collected and sorted your data, it's time to step back and evaluate your design. What did your lander do well? Where did it struggle? Pause the video now and take a few minutes to reflect in your notes. What parts of your design worked, and what would you change next time? In your lesson activities, you'll get a chance to complete one of the final steps of the engineering design process, revising and improving your design. Maybe you'll try different materials. Maybe you'll redesign the structure or add a new feature. That's exactly what real engineers do. Over the years, NASA has tested and improved lander designs many times, learning from every test flight, crash, and success. So if your egg cracked, or even if everything went perfectly, don't stop here. Even NASA's designs rarely work perfectly on the first try. Their scientists respond by analyzing, improving, and pushing their designs further. Use what you learned and keep designing. If you keep trying, you'll find a solution. Which brings us to the final step of the engineering design process, sharing the solution. Once you've built a lander that protects your egg, don't keep it a secret. Tell someone how you did it. Sharing your ideas helps others learn, and that's what real engineers do too. Awesome work today. See you next time.